Have you ever stopped to think about how scientists can measure something they literally can't see? In this explainer, we're going to dive into the super clever ways they do just that, measure invisible stuff dissolved in liquid. It's a huge challenge, but the solutions are honestly pretty brilliant.
I mean, think about it. If I gave you a glass of seawater, could you tell me exactly how much salt is in there just by looking? Of course not, right? It's impossible. But this is a massive deal for everything from making life-saving medicines to making sure our drinking water is safe. So how in the world do they do it?
Well, the answer is a technique called precipitation titration. Now, I know it sounds super technical, but the core idea is actually really simple. It's almost like revealing a message written in invisible ink. You add a special liquid to your sample, and that liquid reacts with the invisible substance, causing a solid to just appear out of thin air. Chemists call this a precipitate. And the exact moment that solid shows up, or maybe changes color, that's the signal that cracks the code. It tells you precisely how much of that invisible stuff was there to begin with.
All right, so let's look at our first method. This one's a classic, developed way back in 1856 by a chemist named Carl Friedrich Mohr. It's a foundational technique, and its genius is all about watching for one specific signal, a telltale reddish-brown color that basically screams, "Stop, you found it." So how does it work? Okay, you take a solution of silver nitrate and you start dripping it very slowly into your sample. Right away, poof, this white solid starts to form. That's silver chloride. You just keep adding the silver nitrate, turning all that invisible chloride into this visible white stuff. But here's where the magic happens. The very next drop that you add finds no more chloride left to react with. So what does it do? It goes after the special indicator you added earlier. And bam, you get this sudden reddish-brown color. That's your stop sign. That's what we call the endpoint.
But Mohr's method is a little nitpicky. It has some pretty strict rules. It really only works if your solution is perfectly neutral, so not too acidic and not too basic. If the pH is off, all sorts of other chemical reactions start happening that you don't want, and it just messes up the colors and makes your results totally wrong. So while it's a fantastic tool, it's not the right tool for every job. What do you do when your sample is acidic?
So yeah, what happens when your solution is acidic and Mohr's method is totally off the table? Well, you turn to the Volhard method. This one is really clever. Instead of building up to the answer step by step, it kind of works backwards.
So with Mohr's method, we were super careful, right? Adding just enough of our chemical to find the answer. The Volhard method flips that whole idea on its head. First, you deliberately add way more silver nitrate than you actually need. Just dump it in there. Then, and this is the clever part, you use a second chemical to measure exactly how much of that first chemical was left over. You just subtract the leftover amount from the total you started with, and that tells you exactly how much you used. It's a brilliant indirect approach that we call a back titration.
The key players in this one are different. We use something called ammonium thiocyanate to find that leftover silver, and an indicator called ferric alum. And the endpoint? Oh, you can't miss it. The whole solution suddenly turns this deep blood red color. It's really dramatic.
Now here's a really cool bit of scientific problem solving. It turns out that first white solid we made can actually interfere with the second measurement and throw everything off. So to stop that from happening, chemists either physically filter it out of the solution or, and this is such a neat trick, they add a chemical called nitrobenzene, which puts this tiny protective coating around each particle. It basically makes the particle invisible to the rest of the reaction. It's just a perfect example of the kind of clever thinking you need to get a really accurate measurement.
All right, on to our third and final method, Fajans Method. This one takes a completely different path. It doesn't rely on a second color appearing in the liquid. Instead, it uses an indicator that literally sticks to the surface of the solid we're creating.
Yeah, the big idea here is something called an adsorption indicator. In simple terms, it's a special dye that pretty much ignores everything happening in the solution until the exact moment of the endpoint. Then, and only then, it gets attracted to the surface of the solid particles we've been making all along.
Okay, so check this out. At first, as that white solid is forming, its surface has a negative electrical charge. Think of it like two magnets pushing each other away. That negative charge actively repels our indicator dye. But the very instant all the chloride is gone, the charge on the surface of those particles flips to positive. And what does that do? Well, it acts like a super powerful magnet for our negatively charged dye. The dye rushes in, sticks all over the surface of the solid, and the result is awesome. The solid itself instantly turns pink. It's not the liquid that changes color, it's the solid. How cool is that?
So we've just walked through three really different, really smart ways to measure the invisible. But this isn't just some abstract chemistry puzzle, right? Why does getting this level of precision actually matter in our day-to-day lives?
You know, this table really sums it up nicely. It's like a chemist's toolkit. You've got Mohr's method, your go-to for simple neutral solutions. You've got Volhard's for those trickier acidic ones. And then there's Fajan's with its elegant sticky indicator. Each one is a specialized tool that a scientist picks depending on the exact problem they're trying to solve.
And trust me, these tools get used everywhere. This kind of precise measurement is absolutely critical for making sure our medicines are pure, for testing that the chloride levels in our drinking water are safe, and for all sorts of quality control in the food industry, checking everything from salt content to preservatives. This is the kind of science that directly impacts our health and safety every single day.
So the next time you look at a perfectly clear glass of water or take a medication that you trust to work, just remember the incredible, invisible science that's happening behind the scenes. It really makes you wonder, what other vital, unseen things are scientists measuring all around us right this very second?